Okay, and welcome back to MacNab Chemistry. Today we're going to have a look at how we can synthesize carboxylic acids from acid anhydrides and water. Okay, so far we've synthesized acid anhydrides from acyl chlorides and water, and we're going to have a look at how we do this, how we synthesize carboxylic acids from acid anhydrides and water. Okay, so the mechanism then for this reaction is a nucleophilic addition elimination mechanism and follows the same pattern of events as the reaction between acyl chlorides and water. The only difference is the byproduct that is produced. Okay, so firstly it's useful to consider the similarities and differences between acyl chloride molecules and acid anhydride molecules, because if we understand the reactions of acyl chlorides with water, then we're going to be able to understand the reaction of the acid anhydride with the water, because actually the mechanism is just the same, it's just that we get this different byproduct. Okay, so here we have it. If I was to take ethanoyl chloride, it would look like this, so CH3COCl. Okay, ethanoic anhydride is, I've got a CH3 here, CO, okay, so that's the same, CH3CO, CH3CO, but then where I had the Cl on the ethanol chloride, I've got this bit here on my acid anhydride, so I've got my CH3COO. Okay, so whenever you're looking at acid anhydrides, if you fully understand the reactions of acyl chlorides, in your mind you just look at this little bit here and think, oh well, that's just going to behave like the Cl behaved in the acyl chloride. Okay, so let's just look at that again. So this is the similarity between the two molecules, the CH3CO, CH3CO. The difference between the acyl chloride and the acid anhydride is this group here. So in the acyl chloride we've got a Cl there, in the acid anhydride we've got a CH3COO here. Okay, so if you think back to the acyl chloride reactions, when we eliminated the Cl, well, as the reactions follow exactly the same mechanism, when we use ethanoic anhydride or an acid anhydride as one of our reactants, instead of eliminating the Cl, we're going to eliminate this CH3COO group. Okay, so when eliminated, this Cl becomes Cl minus, so that covalent bond there breaks, doesn't it? Okay, and that becomes Cl minus. This covalent bond here in the acid anhydride breaks, that covalent bond breaks, so this is this bit here, that covalent bond breaks. Okay, so we end up with CH3COO minus, CH3COO minus, CH3COO minus, that's eliminated. Okay, and then remember also in that elimination stage, in both of these, we lost a H+, so H+ is also eliminated, and therefore the overall byproduct when you're doing the acyl chloride reaction is going to be HCl, H+ that is eliminated and the Cl minus that's eliminated come together to make HCl. And with the acid anhydride, the H+ is also eliminated. We'll look at that in a minute again. Okay, the H+ is eliminated, but also you've got your CH3COO minus eliminated. When H+ comes together with CH3COO minus, you end up with CH3COOH. Okay, so I hope you can see there are an awful lot of similarities between the mechanisms for addition elimination reactions of acyl chlorides and acid anhydrides. Okay, so let's have a look at this in more detail now. Right, let's do a direct comparison then for the reactions of water with ethanoyl chloride and then water with ethanoic anhydride. Okay, I'm just trying to emphasize the similarities between these two processes. Okay, because if you understand the overall mechanism for just one acyl chloride reaction, every single addition elimination reaction can be worked out. You don't have to actually learn any of the other reactions. You can just understand what's going on basically and apply what you know. Okay, right, so let's remind ourselves of the mechanism for the reaction between ethanoyl chloride and water. So ethanoyl chloride is an acyl chloride, and we're reacting that with water, which is behaving as a nucleophile. Okay, this is an acylation reaction, if you remember back to the previous video, and the type of mechanism is a nucleophilic addition elimination reaction. There's my nucleophile, we add it to the acyl chloride, so there's the nucleophilic addition part, and then we eliminate the Cl- and the H+. Okay. Okay, so there's the nucleophile, attacks the delta positive carbon of the carbonyl group there. Okay, the water, this is the intermediate, it joins onto that carbon. Okay, we've got too many bonds coming off that oxygen, so we put a plus on it. That's a good way of remembering that. If you've got too many bonds coming off an atom, then we need to put a plus on it. We don't need to understand any more than that. Okay, how have we been able to create that bond? Well, we've been able to create that bond because we had a double bond there, didn't we? Okay, so that double bond opens out, okay, joins onto there, but that makes that O minus. Okay, so we've got a positive end of the intermediate and we've got a negative end of the intermediate, so clearly this negative charge is going to be attracted through the molecule this way. As the negative charge is attracted through the molecule this way, it causes that electron pair to be repelled, weakening that bond, so that is then eliminated, that falls off. Okay, so minus Cl minus, okay, we end up with this, don't we? We're going to do our intermediate in 2 stages here. Okay, and then this positive here attracts the electron density in between that O and that H bond, or it could be that O and that H, it doesn't matter, they're both the same. Okay, so that positive attracts the electron density in that bond there, weakening it, breaking it, causing the H+ to fall off, okay, or to be eliminated. So if we've eliminated Cl minus and we've eliminated H+, then our byproduct is HCl. So we ended up with ethanoic acid, CH3, COOH, okay, CH3COOH, okay, plus HCl byproduct. So that's the reaction of water with ethanoyl chloride. But let's have a look at the reaction now of water with ethanoic anhydride. It's exactly the same mechanism. Okay, so here we go. Here's my ethanoic anhydride, CH3COO, CH3CO. Okay, the water, the nucleophile attacks the delta positive carbon of the carbonyl group. Now, this some people, when they look at this, they say, oh well, could it not attack that delta positive carbon? Yes, it could. It can attack either that one or that one. It doesn't make any difference because they're exactly the same. We've got complete symmetry in that molecule there. Okay, running across here, got a line of symmetry there. Okay, so yeah, it's all exactly the same. The electron distribution across the molecule is the same, so it could be that carbon or that carbon, it doesn't make any difference. Okay, right, so the nucleophile attacks that delta positive carbon, okay, and it joins on, doesn't it? It adds nucleophilic addition. Okay, it adds by using some of the electrons in that carbon oxygen double bond, so that becomes a single bond. So it's added on there, it becomes a single bond, O minus. Okay, there are too many bonds on that oxygen, so 1, 2, 3, we'd like to have 2, so that becomes a positive. Okay, then this positive attracts electron density through the molecule here. Okay, causing the electrons here, as the electron density is attracted through there, it repels the electrons here, weakening that bond, causing this to drop off or be eliminated. So we then eliminate the CH3COO-, that's this bit, is eliminated, the H+ is eliminated, and what do we end up? We end up with CH3COOH. Okay, we've got rid of all of that and we've got rid of that. Okay, and then also we end up with a byproduct of, just so happens, the H+ and CH3COO-, we end up with a byproduct of ethanoic acid again. So actually we end up with 2 molecules of ethanoic acid from this reaction, whereas in the acyl chloride reaction we only ended up with 1 molecule of ethanoic acid. Okay, let's just make absolutely sure that we understand what's going on with the intermediate steps in this reaction. Let's just get that focus a bit better. There we go. Right, so compare the intermediate steps for the acyl chloride reaction and the acid anhydride reaction. Let's just look at the intermediates and how we drew them. Okay, so we could draw one intermediate showing 3 arrows. Okay, that's probably the easiest way to do it. Okay, and particularly when you're learning, you can just remember then that your intermediates need to have 3 arrows on them. Okay, so these are the 3 arrows. Okay, once that water is added to the C double bond O group, it causes that C double bond O group to become a C single bond O with a minus negative charge on it. Okay, so there we go. The oxygen of the water has got 1, 2, 3 bonds. It only likes to have 2 normally. Okay, so therefore we've got a positive on there. Right, okay, so this positive attracts that electron density through there, doesn't it? Repelling those electrons there, causing that to be eliminated. Okay, so 3 arrows, 1, 2, and then 3. I always link those up in my mind. When this comes, these electrons get drawn down to here, they affect those there. Okay, so they're sort of linked in my mind. Okay, and then that one's kind of a little bit separate, really, it does its own thing. Okay, so there we go. That. Okay, eliminate Cl minus, eliminate H plus. What do I end up with? Ethanoic acid, CH3COOH. In the acid anhydride intermediate, same thing happens. Water joins onto the C double bond O group. It splits the double bond, causing the CO to become CO minus. Okay, what are my 3 arrows? 1, 2, 3. These two are linked, 1, 2, and then 3 is kind of separate in my mind. Okay, what do I end up with? 2 molecules of ethanoic acid. Well, 1 molecule of ethanoic acid, CH3COOH, and then from my byproduct, CH3COO minus, which is all this bit, and the H plus, which was that bit, they come together to make another ethanoic acid molecule. Right, okay, so in conclusion, let's just make absolutely sure we've understood this mechanism, because once we understand it, we can just then apply it to all the others, and they're all the same. Okay, right, so in conclusion, now that we can visualize the intermediates formed with acid anhydride addition-elimination reactions, let's look at the overall mechanism for the reaction between water and ethanoic anhydride, CH3CO, 2 of these and an O. CH3CO, 1, CH3CO, 2 of them, joined by the O. CH3CO2, joined by the O. Okay, so the water, the nucleophile, attacks the delta positive carbon there, doesn't it? Okay, it adds on, so it's nucleophilic addition. Okay, and then we get this intermediate here. Okay, so the water's added on, too many bonds on the water, so it becomes a positive. We've broken the C double bond O group, haven't we? Okay, so that becomes C single bond O with a minus charge on it. Okay, this positive causes electron density to get dragged towards it. Okay, when this comes down here, it repels the electrons in there, this falls off, so there we go. These two are linked, then that's separate in your mind. Okay, what do we eliminate? Well, we eliminate CH3COO minus, CH3COO minus. We also eliminate a H plus. Okay, our main product then is CH3COOH, CH3COOH, and a byproduct of also CH3COOH, so ethanoic acid. So we end up with 2 molecules of ethanoic acid from this nucleophilic addition-elimination reaction. Okay, that is the reaction mechanism and hopefully the understanding for the reaction between water and ethanoic anhydride. Okay, that's it for today, and I hope that's been helpful. Please don't forget to like and subscribe and click on the bell notification to stay fully updated.